Hello friends, in previous video we have seen the design procedure of flange coupling and various notations and various formulas regarding designing of flange coupling. Now in this video I am bringing towards you that numerical on flange coupling, that how to solve numerical problem on flange coupling. Let's see. Problem is, I am reading problem, please try to understand. A flange coupling is used to transmit 20 kilowatt power at 700 rpm. The flanges are of cast iron and other parts are of mild steel. See guys, what it is written here, the flanges are of cast iron and other parts are of mild steel. Determine diameter of shaft, diameter of bolts, assuming number of bolts are 6 and flange dimension. See guys, take shear stress for mild steel is equals to 40 Newton per mm square, shear stress for cast iron is equals to 10 Newton per mm square, tensile and crushing stress is equals to 100 Newton per mm square. See guys, all these stresses are given and what condition they have made us? The flanges are of cast iron and other parts are of mild steel. So only flanges are made up of cast iron and rest of the parts are made up of mild steel. So keep this thing in your mind. Let's see that how it is helpful to us. And they have tells us to assume the number of bolts is equals to 6 and flange dimension. Okay, and the coupling is used to transmit 20 kilowatt power at 700 rpm. So let's start the solution, and we know what is the first step of solution is. The first step of solution is to write given data as it is. Okay, so they have given P is equals to 20 kilowatt, so we need to convert it into watt, that is 20 to 10 raised to 3 watt. Then capital N shows RPM, that is RPM, revolution per minute. The shaft rotates at coupling which is used to transmit 20 kilowatt power at 700 rpm. So N is equals to 700 rpm. Then tau mild, please see, this is tau symbol and this is I have written mild. Why mild? Because there are two different materials are given, because flanges are made up of cast iron and other parts are made up of mild steel. So for mild steel, see guys, shear stress for mild steel is given 40 Newton per mm square, so I have mentioned it here, and shear stress for cast iron is given 10 Newton per mm square. Okay, then sigma T is equals to sigma C, tensile and crushing stress, both value for both the tensile as well as crushing stress is given 100 Newton per mm square. Okay, both shear and tensile stresses is of 100 Newton per mm square. So I have write all the given data first, and then I am starting to solve the numerical according to the step number 1. See guys, so what is the step number 1? Step number 1 is to find out the torque acting on the shaft. This is the step number 1 of flange coupling. To solve the for designing of flange coupling, the step number 1 is to find the torque acting on the shaft. Please see, so formula for that is T is equals to P into 60 upon 2 pi N. Okay, that is why I am putting the all value 22 raised to 3 into 60 by 2 pi into 700. So I am left with the 272.80 Newton meter. So I converted it into 272.80 into 10 raised to 3 Newton mm, because my power is in watts, so I have to the value which is getting the torque which is getting in Newton meter, but in actual calculation we required it in Newton mm. So that is why I have converted into Newton mm by multiplying by 10 raised to 3. Okay, so the torque value is 272.80 into 10 raised to 3 Newton mm. Then in this way we have completed step number 1 and we have calculated the torque required. Now step number 2 is, see guys, step number 2 is to find the diameter of shaft to transmit required torque. See guys, to find the diameter of shaft to transmit required torque. This is the step number 2 of design of flange coupling. So T is equals to, what is the relation for that? T is equals to pi by 16 into tau into d cube. Okay, T is equals to pi by 16 into tau into d cube. So by this relation I have calculated the diameter D is equals to 32.62 mm. I have taken it roundedly is equals to 35 mm. You can also take it to 33 or 34 mm, but for safer condition, for safe side, I have taken it to the 35 mm. Okay, so D I have calculated 32.62 mm, and for safe size rounded value I have taken 35 mm. So in this way we have completed step number 1, that is we have found out the torque and we have found out the diameter of shaft required to transmit the torque, and it will be 35 mm. Now step number 3 tells us we need to fix some dimensions by using standard empirical relations. So we have calculated diameter of shaft as 35 mm. So that is the empirical relation is capital D is equals to twice D into 2 into 35, that is 70 D1 is equal to 3D, that is 105 mm. D2 is equals to 40, that is 140 mm. Small l is equals to 1.5 times of D, so it will be 52.5 mm. TF is equals to 0.5 times D, so it will be 17.5 mm, and TP is equals to 0.25 times D into is equals to 8.75 mm. So see guys, this we have fixed all these empirical relations as calculated diameter. Then next is, this is step number 3B, that is check shear stress in hub. See guys, check shear stress in hub. So for what is the relation for that? T is equals to pi by 16 into tau c into d cube into 1 minus k raised to power 4. This relation we have seen in previous video, that is design of flange coupling. Then pi by 16 into tau c into d cube is into 1 minus k raised to power 4. Put the value d is equals to 70 mm instead of d is equals to 35 mm. So I have put all this value, okay, all this value in the relation, and what will be the answer? So where k is equals to, value of k is small d upon capital D. This we have seen in design procedure. What will be the value is that induced shear stresses, okay, that induced shear stress in hub should be less than your allowable shear stress for safe design. Now see guys, this hub, so induced shear stress, we need to compare it with which value? That is the shear stress value which is given for mild steel, because we are designing hub, and in numerical, if you see, please see here, in numerical shear stress for mild steel is 40 Newton per mm square. Okay, so whatever will be the value, that we need to compare it with this 40 Newton per mm square, because they have clearly mentioned the flanges are of cast iron and other parts of mild steel. So we are designing hub, so hubs are made up of mild steel, so we need to compare it with the 40 Newton per mm square shear stress. Whenever we are designing flanges, at that time we need to compare it with the shear stress given for flange material. Okay, so in this case we need to compare it for hub material, that is mild steel material, and what will be the value, that value should be less than allowable shear stress for safe design condition. Next is step number C, is check shear stress in the flange. Okay, check shear stress in the flange. Now flange is made up of cast iron. Okay, keep this thing in your mind, because they have put condition in numerical. So force is equals to area resisting stress, therefore T upon D by 2 is equals to pi into D into TF into tau. So we have put all these value in this numerical formula, and we have calculated tau. So induced shear stress should be less than allowable shear stress, but this induced shear stress value, you need to compare the shear stress for cast iron material. Okay, the value given, whatever will be the value given for shear stress for cast iron, that cast iron value you need to compare with this value. Okay, because flanges are made up of cast iron, and we are checking the stress in the flange, and flange is made up of cast iron. So you need to compare it with the 10 Newton per mm square, because shear stress for cast iron is given 10 Newton per mm square. This shear stress is a allowable shear stress, and according to safe design condition, what they have said, induced shear stress should be less than allowable shear stress. Okay, I have not calculated the value, because it is better practice for you. If you do this calculation, then that will be helpful for you to understand more clearly. The step number 4 is design of key. So empirical relation. So we need to fix some empirical relation first. W is equals to T is equals to D by 4. So as crushing stress is twice the shear stress, that is why we have used this W is equal to T is equals to D by 4, because crushing stress is twice the shear stress. Let's see how it is possible. It is given in the numerical. You can see your crushing stress value is 100 Newton per mm square, and shear stress value is 40 Newton per mm square. So it means that crushing stress value is twice the shear stress value. That is why we are given this. So W is equals to T is equals to 35 upon 4. It will be 8.75 mm. Length of key is equals to length of flange. Therefore small l is equals to 52.5 mm. Then fourth B step is check shear stress induced in the key. So relation for that is T upon D upon 2 is equals to W into L into tau. So we have put all these value here, and we have calculated whatever will be the calculated value for this tau, that should be less than shear stress for key. And shear stress for keys are made up of mild steel. Only flanges are made up of cast iron, okay, and other parts are made up of mild steel. So your induced shear stress value should be less than allowable shear stress for safe design. What is the step C? Check crushing stress induced in the key. So T divided by D by 2 is equals to T by 2 into L into sigma C. Find out this sigma C induced crushing stress, and it should be less than your allowable crushing stress. Okay, so I have not calculated the actual values. This is good practice for you. If you are trying it, then you will be definitely understand that how to calculate the various answers. Then step number 5 is design of bolts. See guys, so what is the step A? Number of bolts. N is equals to 4 as diameter of shaft is up to D less than 55 mm. This is the condition that we have seen in previous video in our design procedure of flange coupling. So D when your calculate diameter is less than 55 mm, at that time you need to take N is equals to 4 and B is equals to shear failure of bolts. So what is the relation for that? T upon D1 upon 2 into N into pi by 4 into DC square into tau. So by this relation your DC will be determined easily, and once you calculated the value of DC, so DO, then DO is equals to DC upon 0.84. By this you can easily calculate the value of DO, and in this way you have successfully calculated all the dimensions for flange coupling. I hope this content is useful for you. Thank you.